Okay, we're back and we're computing the posterior distribution for the mean of a univariate Gaussian. Right, so let's go back here, remind ourselves quickly what we're doing. So we're getting the posterior distribution, this thing. So it's just the distribution on mu given our data. So we wrote that this was proportional to some stuff here, and we pulled together the exponents, and then we were looking at the exponents, and we did a lot of little calculations here. We were trying to get it in this form because we wanted to get it in the form of a Gaussian distribution. So this would give it in the form of a Gaussian, and we got that form, right? So this would be the D here. And so we would like to match this up. So we want to match this up with what a Gaussian, the exponent in a Gaussian, looks like, and that's that's minus 1 over 2 sigma squared. Let's call it sigma n squared times mu minus the mean. Let's call that, well, we'll call it m. We'll just keep it like that, m squared. So we've got m. Oh, and well, there's going to be a constant, right? That's fine. Keep that, c prime. So the only thing we need is we need to take sigma n squared to be 1 over this guy. So let's do that. So we can achieve this goal if we take, so we'll take sigma n squared equal to 1 over this. So I guess I'll just go ahead and write that. 1 over sigma naught squared plus n over sigma squared. This is going to be the variance of our distribution. And m, maybe I'll call it mn to emphasize the dependence on n. So this is going to be mn. Mn is, that was this thing, and so the denominator is 1 over sigma n squared, so this is equal to sigma n squared times mu naught divided by sigma naught squared plus this sum of the xi's divided by sigma squared. So let's simplify this a little bit here. Let's write this as, let's see, how do we want to do this? So I'm going to continue this line here. This is the mean. Let's see, how do we want to do this? I want to express it in terms of as a convex combination of mu naught and this sum here. Just to emphasize. Well, maybe I'll come back to that in a sec. So we've got these here, and this. So we've got it now, right? We're in good shape because as a function of mu, right? So let's write it all out now. So the probability of mu given the data equals, since this is the exponent here, and since e to this is proportional. That's the stuff we were just proving. We were proving that e to this as a function of mu, e to that, is proportional to the probability of mu given the data. So we have that, I'll write it this way, probability of mu given the data is proportional to e to the minus 1 over 2 sigma n squared times mu minus m squared, mn, I guess I said. And since a function that's proportional to the distribution uniquely determines it, then in fact this is equal to the Gaussian. So this implies that, that mu, the posterior distribution on mu, sometimes we write like this, is distributed as a normal with mean mn and variance sigma n squared. So this posterior distribution, you just put 1 over square root of 2 pi sigma n squared. And we've got it. So this shows that the posterior distribution for a univariate, the mean of a univariate Gaussian, where we put a Gaussian mean on a Gaussian prior on the mean, the posterior distribution is also normal, and it has this mean and variance. So something to note about this variance, something which is a cool little mathematical fact, is that this, if you were to multiply this by n plus 1, I guess here, then it equals the harmonic mean of the numbers sigma naught squared, sigma squared, sigma squared, and sigma squared n times. So that's a nifty little way to remember this identity here. It's harmonic mean of these numbers times or divided by n plus 1, that is. So that's nice. And this part here, it's the mean of the posterior distribution, and in fact this also equals the map estimate for mu, because it's the maximum a posteriori, because in this case for a Gaussian the maximum of the distribution, it occurs at the mean. So let's write this out in a slightly different way. This is what I was about to do a second ago. Let me change colors here. To observe that it's actually a convex combination of the prior and the MLE. So Mn equals, let's see, how do we want to do this? I guess we can just let's just try this. So it's just sigma n squared over sigma naught squared times mu naught, plus, if we divide and multiply by n, then we can get the MLE, the sample mean. So it's going to be sigma n squared divided by sigma squared times n times the sample mean, which is the MLE, right? The MLE is just 1 over n times the sum of the xi's. It's the sample mean. So let's see, I said that this should be a convex combination, so the sum of these ought to be 1. So maybe we should check that just to be sure. So if we sum this with this, of course we just pull out the first guy. We get n over sigma squared plus 1 over sigma naught squared, and sigma n squared is sigma n squared is 1 over that thing. So it's just, right, sorry, you can't quite see them both at the same time, but sigma n squared is 1 over this. So these cancel and we get 1. So in fact, this is a convex combination here. This is a convex combination of mu naught and the MLE. So it's a nice interpretation of this, and that's an important fact. And I'll draw a picture of that in a second, but I wanted to first, yeah. So we'll draw the picture here. Okay. So here's the picture. Say this is this is an axis for mu, and let's say that our prior mean is here. This is our prior mean. And maybe the MLE is over here. So what this says, it's a convex combination, so it's somewhere on the line, the straight line between these two. In this case, they're just, they're just real valued numbers, so it's just somewhere between these two on this interval. And if you take so we can draw it here. So it's somewhere, maybe it's here. So, or rather, that's MN is the posterior mean, or the map. So the prior, if we were to draw the prior distribution, our prior distribution, remember, it was a Gaussian with mean mu naught. And it had some variance, sigma naught, so it looks something like this. Some nice Gaussian. And the posterior mean here, the map, the mean, the posterior distribution of the mean has variance sigma n squared. And if we look at this guy, as n goes, so let's see. So if n is 0, then it's just sigma naught squared, right? It's just the prior variance. So that's nice. So when we have no data, we just revert to the prior. As n goes to infinity, then what does this become? If we multiplied by sigma squared and sigma squared, then we would see that this is going to, it's going to 0, of course. As n goes to infinity, then this is going to 0. So the prior, or rather the posterior distribution, has a variance which is becoming smaller as n increases. So we have this would be our prior, and then as we get a little bit of data, maybe it looks like this. Maybe we get a little bit more data, and it's getting even sharper. And we get more and more data, and finally, it's going to converge to something. It's going to converges to a point mass. Well, that's not quite a point mass, but it's getting more and more peaked. It's Gaussian all the time. And in fact, it converges to the same thing as the MLE, which we can see from this expression here. So the MLE might not converge to this, but the MLE is converging to something. And so how can we see that? Let's see. I could have written this out in terms of this, but let's see if we can just see it. So as n goes to infinity, right, as n goes to infinity, we know that this is going to 0, right? That was our earlier observation. This thing goes to 0. The sigma n squared goes to 0. So the contribution in this convex combination from the prior mean is getting washed out. It's going to 0. It's going to nothing. And so all of this mn, let's see, so if we multiplied this by n, we would have n, what would happen here? N, or we can make it, put 1 over, instead 1 over n on the bottom. Yeah, then that would cancel here. So then this would go to 0. And in fact, it would converge to the same thing as the MLE. You can check that little calculation there. It's a simple thing. So it turns out that Mn is going to converge to the same thing as the MLE as n goes to infinity. And the MLE is consistent, in fact. We haven't proven that. But that means that the posterior distribution will concentrate to a point mass at the true value.